And the classification rule is for test input data point X, assign most common label among is K most similar training inputs, and K is neighborhood. Or K could be any number, but usually K's are in odd, but not in multiple of classes that we are trying to classify. और odd की होने की वजह ये कि we want to have majority voting. So once we have odd number, it's easy to find who is the winner class. And formally, we can define kNN as, let's say we have given a test point X, and K nearest neighbor set is denoted as Sx for point X. So Sx is set of all the neighbors, nearby neighbors for point test point X, and Sx is subset of D, which is our data set, such that cardinality of Sx is equal to K. So they are exactly K neighbors or K data points in it. So it's not approximate, it's exact K. And for all X prime, Y prime that are in D but not in Sx. So for all the data points in our data set which are not part of neighborhood set, they have distance greater than or equal to maximum distance of neighborhood points. This is how it is. So all the points which are not nearby or in the neighborhood set are our minimum distance is greater than maximum distance of neighborhood points. Or in other words, we can say that for every point in D but not in Sx, so neighborhood set is at least as far away from X as the farthest point in neighborhood set. Right, so this is just to say mathematically that nearby points are part of neighborhood set. Then we started looking at distance metric because all the notion of kNN classifier is based on distances. So here also आप अगर देखें on your slide, so distance of nearby point is neighborhood points is greater than the maximum point, greater than or less than जो आपके neighborhood points है. So this is all based on notion of distance metric. And if we have perfect distance metric which gives result based on data points, then we have perfect classifier. But we don't have perfect distance metric based on different kind of data sets, right? So we started looking at Minkowski distance family. This is generic form of Minkowski distance, and we can replace this P with numbers and we will have different distance metric. And last time we looked at it, if P equal to 1, then distance would be Manhattan's distance, most commonly used. This is also called L1 norm or earth mover distance. If P equal to 2, we'll get Euclidean distance or L2 norm. And if P goes to maximum, we get Chebyshev distance or maximum difference. Any point up till now? Any query up till now which is not clear?
No, sir, clear.
Okay. Okay. So this is the intuition of difference distance metric. So this red, blue and yellow line belongs to L1 norm or Manhattan's distance or earth mover distance, and green line is Euclidean distance. And we did this small example as well in our last class. Then we looked at this toy data set and we tried to find classification for this data point based on this toy data set based on Euclidean distance. This is how we can plot it. I showed you how we can do it in Python, very simple. This is how we plot it. And if we have a test query point, we we'll just find the distance to all the points from this query point. And if we are looking to k equal to 1, let's say for one neighborhood, we'll find the nearest point in this example, probably this is the nearest point, and we give its label to the test query. If we have three, then we will look into different three nearby points and we will do majority voting. Let's say if point is over here, probably this is nearby point, this is nearby point, and this is nearby point. But then we will have a majority voting and still we'll get this red class label. And again, I showed you Python code for it, how we can do it. So this is with you. You can just code it yourself to see how we are getting results. Again, this is result of Python. Class 1 was class red. Okay, so we start. This is the notion of nearest neighbor classifier. And again, we say that if we can represent image in feature space like a data point, it's easy for us to just classify. So we started looking at this MNIST or digits data set. And if we know how to calculate distance from point, query point to all the points in our data set, which are images, then we can classify our test query image as well, like in this case, based on minimum distance. So this was the data set I used in last class as a toy data set, which is called digits, and it's available in sklearn or scikit-learn library of Python. These are example images of sklearn. Dr. Shaisa, please mute your mic. The problem was how we can represent image in our feature space. So we could have n-dimensional feature space. Usually we are used to looking at two-dimensional and three-dimensional spaces, which are like this, but it's difficult to visualize more than three dimension. But mathematically, it's possible to have n-dimension, 1,000 dimension, 100,000 dimension feature space. And if we don't have feature extractor, then we can just simply use pixel values as features, and this is what we did in our last class as well. So we used this pixel values as features of an image and plotted them in our feature space like this, and we calculated distance like in our toy example we did. We use same distances. So this is how two images are same distance I got is 31.98 from Euclidean distance, and if images are different, I get different Euclidean distance, which is more than 0, 0. So we have some notion of similarity even if we use pixel values directly as features. And then we started looking at how we can do it in Python. So again, I work with this digits dataset, which is available in sklearn. So this was the test image. And again, these are the steps of kNN algorithm. And formally, I will show you the algorithm, but this is again the same step. Find distance to all find point with minimum distance and assign label of nearest point. So this is just one NN. So it's one nearest neighbor. So if we have three NN, we could have three nearest neighbor and we assign majority voting. Right. Up till now, and in that we looked at, we just trained on 10 images and tested it only on one image. Then I tested on 100 images and training was only on 10 images. So that was the problem. And our training error bumped from 3 to 37. And then I asked you how we can improve its accuracy. And there were few ideas and we worked on one of the idea. So the idea one was we have used only 10 training examples to train. Why not to have more samples? So 10 training samples will not capture all the variations of different classes in data. So if we have more data, we could have more robust classifier. Idea two, to have more neighbors because we could have noise in our data, and if we are just looking at one neighbor, then we are overfitting to the data, or we have more like we are 100% confident the data is sharp and clear, but this is always not the case. So we could have more neighbors to have more generalized classifier. And idea three was to change distance metric, and if you don't want to use Minkowski distance, we have different distance metric and we can just try them as well. So this was idea number two, I guess, adding more training samples. No, this was idea one, adding more training samples, and we started training with more training samples. And this is kind of a curve that we got from that MATLAB Python code, which I coded, and I coded different distance metric as well. So we have So distance for difference was not huge if we use different distance metric, but still it has an impact. And we can see that when we have more training samples, classifier is getting more robust and errors are getting less. So this was kind of a exercise which I did in last class. And then we took idea two to add more neighborhood in our algorithm. And I gave you this two example. So let's say if you are just looking at one nearest neighbor, so this is the nearest data point to the query image, and we can just draw a radius, a circle around it, and to see we don't have any other data point nearby, and we'll just assign its label to the query point, and label over here is diamond. So test query data point will get label of diamond. But if we add more neighbors, so three nearest points, so these three are nearest point, and if we just, this is kind of a circle that encapsulates these three nearest data point, and we'll do majority voting, and in this case our classification result will change from diamond to star. So this is the impact of adding more nearest point or nearest neighbor. And if we have k equal to 7, our classification is the same, so there is no change. So it's again domain dependent. What should be right value of k? There's whole lot of research area to find exact k for a different data set, but it could be found empirically if you are doing some practical examples. So this is formally how we can write k nearest neighbor classifier algorithm. So out of n training vectors, identify k nearest neighbor. So k again is a metric or hyperparameter that we can tune. The portion is case chosen to be odd, and I have given you the reason that we are doing majority voting, and if we have odd number of votes, then it's easy to find who is the winner. If we have even, we could get result of 50-50, then we'll not know which is winner class. Right. So out of k samples or k nearest point, identify number of ki vectors that belong to class wi. So again, we are trying to find which is majority class in neighborhood and assign that wi class to this test query vector. So that is simply formally saying the same thing which we are doing it for last week. Okay, so k, it's a parameter that has to be learned. It has domain knowledge. It depends on domain knowledge. And again, I give you example. If I use k equal to 1, I get diamond as a classification result for this test query point, which is x over here. If I use k equal to 3, I get star because 3 nearest majority votes in 3 nearest neighbor is class star. But if we increase it to 7, I'll get back the same result as diamond. This is to show that if we are increasing, we could have varying results. And I'm not sure which is the right result, whether it's test query point is diamond or star, or if there is any other class. So k has to be learned. It's a hyperparameter. It has to be tuned. And we looked at improvement because the idea is that nearest point should have more weight in voting because it's nearby. If we keep on adding more Ks or more neighboring point, we will have different result. But if nearby points have more weights, then probably we'll have more confidence on the data, and we can just calculate weight of each data point which is in neighborhood class or set Sx, which we looked at initially. We can just calculate weight using this formula, right? And then we can do majority voting. So this will somehow reflect on noisy data as well. But it's like a good match because we are giving more weight to nearby classes. But if it's a noise, then probably all other points nearby this point would be star. So even if we have more Ks, we'll get star over here. If this is a noise point, because then this diamond would only be just one point over here. So by doing this, we are sure that we'll cater noise in our data set. Any question up till now?
नहीं सर कोई क्वेश्चन नहीं है
Okay. Okay, okay. And then we start looking at computational complexity of k nearest neighbor classifier. And we just had this in last class that training complexity, actually there is no training complexity, is just recording the data. So there is no training happening, but test complexity is linear to the number of n or number of samples and their dimension. So this is not a good classifier. And if we just plot this linear curve, it goes like this. So it means that if we have more data, then our classifier complexity is increasing, which is not good. It should be independent of number of points because in machine learning, we are looking for more data points to have robust classifier. But here we are looking at that once we start adding data to our model, then this classifier will have a very late response. So this is not good. It's linear to the number of samples and their dimensions. And then I asked you like any suggestion to make it fast to reduce its complexity. And then there are few of tricks or optimizations that we can do on kNN to make it more fast or more robust. So number one is reduce dimensions by removing irrelevant features. And in kNN, more dimension means this is a curse. And I will explain in few slides why I'm saying it's a curse. But if we just reduce number of dimensions or irrelevant feature, our classifier would be a bit faster because it's big O of N and D. So we can reduce its complexity by reducing D or searching N very fast, right? So this is one of the thing that we can reduce D. And we can reduce N not in a sense that we'll delete the data, but we'll not compare all N's when we'll trying to find nearest neighbor. And I will explain this as well, these 2 points in today's lecture, how we can do it. So if we find, let's say we have n data points and we know that only m are potential nearest neighbor and m is far far less than n, then we'll have a speed up in runtime of kNN algorithm. But then we have to find this potential neighborhood points m, and this there is a complete whole lot of field how we can find m. So one of the thing is k-D trees. It's a data structure, or for computer science students, it's depth first search trees, or DFS as we call them. This is the data structure to store our data points in such a way that it's easy and it's very fast to find neighboring points. And I will explain how. But it's not perfect and it can miss neighbors. There is another data structure called inverted list. We have hashing as well that can be used to speed up neighboring search. So these all techniques will speed up search time. And again, what is the inductive bias of kNN classifier? As you, and kNN inductive bias correspond to assumption that classification of test point will be more similar to classification of other instances that are nearby in Euclidean space, let's say. So points that are similar in feature space are should have same labels. Okay. Now I'm showing you a toy data set in which we have these blue triangles and red circles. So these are true classes. And I want you to visualize or imagine what kind of decision boundary k nearest classifier will induce if we'll run k nearest classifier or k equal to 1 algorithm. If k is 1 and if we run this algorithm on this data set, what kind of decision boundary you'll get? And any answer or any thoughts on this?
सर आप क्वेश्चन रिपीट कर सकते हो?
I'm showing you this try data set, right? And I'm asking if k equal to 1, what kind of decision boundary k nearest classifier will induce?
सर वो बाउंड्री तो कुछ ऐसी होगी ना कि सारे राइट पे सारे रेड पॉइंट्स आ जाएंगे और लेफ्ट पे सारे ब्लू.
Will it be a linear line or what kind of boundary? Or it will be like a circle or some polygon or what kind of surface it would be?
कर्व होगा.
Actually, kNN जब भी इंड्यूस करता है, it induces normal bisectors or perpendicular bisectors of a point, जो आपने ज्योमेट्री में भी देखे. So it would be like if these two are different points, their normal bisector would be something like this, right? ये क्लियर है आपको? इन दो पॉइंट्स का नॉर्मल बाइसेक्टर वुड बी दिस, then these 2 points, their normal bisector would be like this. If these two are different points, their normal bisector would be like this. So it's something like that. ठीक है, और इन दोनों के अगेन ये दो डिफरेंट है, so this is their normal bisector. So this would be kind of a decision boundary kNN algorithm will induce if k equal to 1. If we have k equal to 3, then normal bisector has to take into account all the neighboring points. But if k equal to 1, it's very easy to visualize what kind of decision boundary kNN algorithm will induce. And this is also called Voronoi diagrams or Voronoi cells. I'm not going into details why it is called like this. But any question from this point?
नहीं सर.
No, sir.
Okay. Now, this is what I have made a small Python demo for you guys to visualize decision boundary. I will show you its code as well. So this is on Iris dataset, which is also available in scikit-learn or sklearn of Python library. And I have used only 2 dimensions for the sake of visualization. Iris has actually 4 dimensions, so I have used first 2 dimensions to visualize class. And this k would change. Initially k equal to 1, and there are 3 classes over here. I don't remember name of classes, but there are different types of iris flowers available in this iris dataset. So these 3 classes are, there is, you can see yellow rounds, blue rounds, and these are light blue, and then there are dark blue rounds. So these are 3 different classes. And if I run this k nearest classifier with k equal to 1, I will induce this kind of decision boundary. These are simply perpendicular bisectors between different class data points. So you can see, let's say these two are different class data points, and this is simply bisector over here, right? Very easy to see. Again, there is bisector over here between these 2 class points. And here you can see this one point is kind of an isolated point, this dark blue point. But when we take k equal to 1, it will have a Voronoi cell or kind of a cell around it, because we are just looking at one nearest neighbor, right? So one nearest neighbor, the issue is we are very confident on the data set that there is no noise. But if we just look visually, probably this seems to be a noisy point, or this doesn't belong to this kind of distribution over here. But if we have k equal to 1, this point will have a different classification result. But once we run it for k equal to 2, so there are 2 nearest neighbor around each point. Previously, this point has a decision boundary around itself. So any point like here, any point between, in this cell will get this dark blue classification result. But once we have k equal to 2, we are generalizing. We are not looking at only one point when creating a decision boundary, but 2 points, 2 nearby points. And once we look at 2 nearby points, we can see that this classification result changes from dark blue to light blue, because this space in our feature space have more votes for this light blue cell, right? So I think this would get clear what is the effect of changing number of neighbors. And once we have k equal to 3, we are even more generalizing. Here you can see that this one point have its own cell around itself. But when k equal to 3, this is gone, and this whole of this area is dark blue. So this is So we are generalizing, we are not very sensitive to the data. So when we increase number of k, we are generalizing on unseen data, let's say. So this is kind of opposite to overfitting. K equal to 1 is actually overfitting. We are really sensitive to the data and we want to exactly model distribution of the data. But once we start loosening up this condition of k, we'll have more generalized decision boundary and even k equal to 4, right? And if you can see, I'll show you. This is the code for generating this kind of boundaries. And if you want to get this code, you can get it from me. I'll just run and show it to you. Okay, it's on the other screen. I'll show the results one by one. Running. So this is the result on k equal to 1, as I showed you on the screen. Then I'll show result for k equal to 2, right? So this was k equal to 1, kind of overfitting the data. K equal to 2 and we are generalizing. K equal to 3. So we are not very sensitive to neighborhood, exact neighborhood, right? And this is k equal to 4, right? So you can just play with different toy data sets to see influence of k on decision boundary and like what is happening in our feature space, right? So I run it for 4 times. You can run it for, let's say, k equal to till 13, and to see actually when you start increasing, you will have like an average label. If k equal to, let's say, 50, you'll get the average label in the feature space, right? So it's like underfitting. Any question from this example?
सर हम k यूजुअली
एक
ऑड नंबर्स में लेते हैं ना, राइट?
Usually k equal odd hota hai, but for this demo I just took like k equal to 1, 2, 3, 4, 5, 6 in sequential order. But generally for practical systems k is odd usually. और उसका रीजन वही था कि मेजॉरिटी वोटिंग में आपको प्रॉब्लम ना हो. k equal to 2 में you could have like 2 votes, one vote for one class and one vote for other class. So it's like 50-50 probability, and classifier is not sure where this test point belong to. But for the sake of demo, I just run it in iterative way.
अच्छा, ठीक है. तो सर एक सवाल ये था कि जैसे हम अगर इवन नंबर पे रन करते हैं क्लासिफायर को, तो
Yeah.
क्या ये पॉसिबिलिटी है कि दो अलग अटेम्प्ट्स में वो अलग-अलग डिसीजन बाउंड्री दे?
k equal to 2 में अलग डिसीजन बाउंड्री नहीं आएगी, बट देयर वुड बी कंफ्यूजन. देयर कुड बी कंफ्यूजन अगेन, जो मैं आपको बता रहा था. तो देन क्लासिफायर विल रैंडमली आउटपुट सम क्लास. इट वी आर नॉट श्योर कि कौन सी क्लास है. लेट्स से वो क्लास 1 का 1 वोट है और क्लास 2 का सेकंड वोट है. तो क्लासिफायर इज नॉट श्योर कि टेस्ट पॉइंट को क्लास 1 में दे या क्लास 2 में क्लासिफाई करे. देन इट वुड
लेकिन
बी
उसके
लाइक रैंडम आउटपुट.
हाँ, मतलब लेकिन उसके रिजल्ट्स कंसिस्टेंट होंगे?
रिजल्ट इट डिपेंड्स कि पाइथन किस तरह उसको कर रहा है या मैटलैब किस तरह कर रहा है. आई एम नॉट श्योर कि इनके बार बार चेंज होता है कि नहीं, बट यूजुअली दिस इज लाइक कंफ्यूजन इन अ क्लासिफायर.
ठीक है सर, थैंक यू.
ओके, एनी अदर क्वेश्चन?
नो सर.
Okay. Okay, now this is like I'm giving you a toy data set, an exercise. There are 3 points in positive class, let's say this class, and 3 points in negative class. And I want you to draw its decision boundary for one nearest neighbor classifier. Right? You just plot those points in Euclidean space, draw their normal bisectors or perpendicular bisectors, and have a decision boundary. You can do it in your copies, in your notebooks. You have 2 minutes. Got it? Dr. Shahid, you can also draw them.
Yes, sir. I'm I'm drawing, but actually I have to go for my lab. Okay, there's PF.
Right.
I'm drawing. I'm drawing.
Osama and Ariba, are you doing it?
Yes, sir.
Okay. Okay. Are you done?
No, sir. The 2 minutes.
I'm showing you this the plot of this data point, so easy to just see where the decision boundary would be.
Excuse me, Dr. साहब.
जी जी
अच्छा, मैं ये कह रहा था कि ये तो हमारे पास ट्रेनिंग एग्जांपल्स है ना, ये जो हमें जो
जी
डेटा
जी
सेट दिया आपने,
जी जी
तो इसमें डिसीजन बाउंड्री हमें किसी टेस्ट एग्जांपल के थ्रू प्लॉट करनी है या वैसे ही?
नहीं, सिंपली यू कैन जस्ट ड्रॉ परपेंडिकुलर बाइसेक्टर्स टू फीड देयर डिसीजन बाउंड्री, जो मैंने अभी पाइथन के
अच्छा
आपको एग्जांपल में दिखाया. देयर वाज नो टेस्ट पॉइंट.
अच्छा, ठीक है. क्या आपसे शेयर
अच्छा
करनी है
उसामा
वो
जो
सर?
आप कह रहे थे कि उसामा जो आप कह रहे थे, एक मिनट में शायद सर, I have run this Python code for different number of k's and you can see result k equal to 1 आपको नजर आ रहा है स्क्रीन पे, राइट?
राइट सर।
नाउ k equal to 3, मैंने अब इसको ऑड के लिए अगेन k equal to 3 तक तो हमने देख लिया था. नाउ even increasing further k equal to 5, आप देखेंगे डिसीजन बाउंड्री k equal to 5 पे स्टार्ट चेंजिंग फ्रॉम ओवर हेयर, ठीक है, क्योंकि नेबरहुड का इन्फ्लुएंस बढ़ता जा रहा है. k equal to 5 and then k equal to 7, k equal to 5 तक ये पॉइंट शायद क्लासिफाई करेक्टली हो रहा था. k equal to 7 पे दिस पॉइंट स्टार्ट गेटिंग मिसक्लासिफाइड, क्योंकि इस रीजन में 7 नेबरहुड में सारे जो है वो ज़्यादातर जो आपके पास लाइट ब्लू कलर के डेटा पॉइंट, ठीक है. उसके बाद k equal to 11, अच्छा 9 भी है बीच में, बट दिस इज k equal to 11, ठीक है. अब आप देखें once we start having k equal to 11, this all of this region is becoming, क्योंकि इस रीजन के जिस जिस जगह पॉइंट पे भी आप जाएंगे 11 नेबरहुड में आपको डार्क ब्लू वाले पॉइंट मिलेंगे, 11 पॉइंट्स. तो दिस लाइट ब्लू कलर इज गेटिंग श्रिंक and now k equal to 15, k equal to 11 में आपको यहाँ पे लाइट ब्लू कलर की क्लास नजर आ रही थी, बट नाउ दिस इज गॉन. k equal to 15 में and then k equal to 17. so this is like generalizing even more. बहुत
राइट सर।
ज़्यादा स्ट्रिक्ट क्लासीफायर से हम एक अनरिस्ट्रिक्टेड किस्म की क्लास की तरफ आते रहे. k equal to 19, बहुत ही स्मूथ हो गई हैं आपकी बाउंड्रीज, बट देयर आर लॉट ऑफ मिसक्लासिफिकेशन, right? So this is like a hyperparameter and you have to see according to the problem in your hand, like what is the right k. Depending on the data set, value of k will change and you can just empirically verify which k gives least test or training errors. So you don't want to overfit, you don't want to underfit, but you want to have the best of both the worlds. So this is like tuning parameters. Yes, Shaisa, you were saying something. Ariba has sent me an image with the decision boundary, which seems kind of okay. आप लोग सब देख सकते हैं. Miss Ariba has sent an answer, and I will also draw mine. Ariba is almost okay. सिर्फ 2-3 जगह पे I'll see some issues, otherwise it's okay. Right. So without looking at the answer, perpendicular bisector of these 2 points should be something like this, something in the middle. ठीक है. Perpendicular bisector of 2 points from 2 different classes again. ठीक है. Something like this. Now इस point और इस point का impact is something like, right? So these two interact over here. These 2 points is perpendicular bisector should be something like this. This is very easy, like straight. And this is something like this. Right? Something like this kind of boundary it would make. Am I clear?
जी सर.
So this is how it would be. जो मैंने draw किया था is almost same. ठीक है? So perpendicular bisectors between points of different classes. That's it. That's you have to draw and you find the decision boundary. So all of this region is red region, and this region over here and this region over here is blue region. So you have like very clear cut boundaries. Is it clear?
यस सर।
तो सर अगर आप k को 2 रखें तो तब भी आप ऐसे ही ड्रॉ करेंगे?
It will be perpendicular bisector bisector, but you have to see, let's say for this point, you will have impact of this and this point. Right now, it's easy to say that perpendicular bisector between these 2 points and then this 2 point. But once k equal to 2, it will have two nearest neighbor. Usually ये वाले नजर आ रहे हैं, not this one. So this point will change. It will be something like this probably over here. ठीक है? So you have to take influence of neighboring point more and more if you increase k. Right. अच्छा, k nearest neighbor को lazy learner भी कहते हैं. Lazy learner in the sense that learning or building model is postponed till query point arrives. So initially, training phase is just saving your data in memory. That's only the training point. और eager learner usually इसकी opposite class है, जिसमें as soon as you have the data, you run it and you build a classifier. In k nearest neighbor, training is postponed till query point or test point arrives, and then all the processing happens. So it has a lot of drawbacks as well with some of the advantages. The key advantage over here is instead of estimating target function once for entire data set, it learns target function for each new instance. So like again, this is positive and negative as well because there is no training. For each training instance, it has to rerun, but then on the other side, it can have different boundary because then it will calculate different nearest neighbor based on the test point. And there are some instance based learning के अंदर कुछ और algorithm भी k nearest neighbor which we did in this class. There is another algorithm called locally weighted regression model. We haven't done regression up till now, and once we see, then you will see that kNN with some modification can be used for regression as well. And case-based reasoning also is a lazy learner, but not included in our curriculum. But there are some set of classifiers that are based on this same ideology. Disadvantage: cost of classifying new instance is high. This is what I'm saying. So nearly all the computation takes place at classification time rather than when training examples are first encountered. So this is problematic. In this way, we want to have results as quick or as soon as possible. So whether it doesn't matter, we'll build the classifier for 10 weeks or 10 months. But once we have a classifier, we want test query to be pass through this all the model, and we get the prediction in real time. And this is how a lot of algorithms are running. Let's take an example of Google or Gmail. They are filtering our spam in real time. And if we use kNN, it means that our mail will arrive and it will process. It will take 1 week, and then we will have a result that whether this email is spam or not. So this is not allowed in real world applications. We could take like different weeks or months to train an algorithm, but once it's trained, we want prediction to be in real time. So this is the bottleneck of kNN, or drawback of lazy learners of kNN, that computation is done once training test point arrives. So this is counterintuitive in real life. And all attributes of instance are considered when attempting to retrieve similar training from memory. And this is another issue with kNN, that probably some of the attributes are not meaningful. But once in kNN, we are calculating this distance based on all the attributes. So then again, we need to find which attribute has to be taken into account when taking the distance metric, right? So there, these two disadvantages are so huge that kNN are usually not used in real world application. But for the sake of completeness and to know theory, like what is how from where machine learning started progressing, so this is one of the most important classifier. Now once I was giving you disadvantages of kNN or practical issues with kNN, one issue term that I coined is curse of dimensionality, and it's very important aspect of kNN, and that we have to look into to understand what is curse of dimensionality. Right. So one practical issue of applying k-nearest neighbor classifier is the distance between instances calculated based on all attribute features. Right. All the dimensions are included in distance metric, and this is contrary to many machine learning algorithms. We haven't done my decision tree up till now, but decision tree just splits tree into 3 dimensions. based on different attributes, and some attributes are never used in calculating or predicting new data. So there is a weighting mechanism to weigh which attribute has to be used, but in k-nearest neighbor there is no mechanism to find weight or importance of different attributes. And considering applying kNN classifier to problem that has 20 features but only 2 attributes are relevant. So this is again an issue and result could be misleading, right? The difficulty which arises when many irrelevant attributes are present is sometimes referred to as curse of dimensionality. So there are a lot of dimension available in our data set, but they're probably not useful and we are using it. It is one of the aspect of curse of dimensionality. But formally, as the number of features or dimensions grow, the amount of data need to generalize accurately grows exponentially. This is curse of dimensionality in formal way. As the number of features or dimensions grow, the amount of data need to generalize accurately grows exponentially. If we have high dimensional feature vector, we'll need infinite numbers of training examples to really generalize well on the training set, right? इसमें कोई issue है to like what is curse of dimensionality? So it means if we have, let's say, 100 dimensional feature vector, जो हम feature vector की बात कर रहे थे, x1 से लेके xn तक और d dimension. If we have like, if d goes to, it goes higher, we'll need infinite amount of data to generalize well. Otherwise it will start overfitting and we'll not have the right results, or we will have very less training error, let's say, but test error would be very high, right? Any issue up till now?
नहीं सर क्लियर.
ठीक है. अच्छा, unfortunately in high dimensional spaces, let's say if we have high dimensional feature vector, points that are drawn from probability distribution tends never to close. This is kind of counterintuitive how we visualize 3D world. Let's say this is example of a cube given in 3D, and we can see that if we draw points randomly, they could be like randomly at different positions. But if we increase dimensions, it's difficult to visualize, but most of the data points are at the corners of different surfaces, and in between surface is space is usually free. So all the data points are at the, so the notion of closeness or nearest neighborhood as used in k-nearest neighbor just diminishes because everything is far away. In high dimensional spaces, usually points are not close, they are very far away. And then I will just explain why I'm saying that mathematically as well. So here I'm giving you example of this hypercube, right? With the unit length. So it is one in each dimension. And now I draw a small cube inside it with length L, and I want to know how big this small cube would be to encapsulate k nearest point, right? If they are drawn randomly. And I will show you that this size will grow exponentially. Formally, this is the unit cube of d dimension, right? All training data is sampled uniformly within this cube. Any issue up till now? I'm just formalizing this example.
No issue.
Okay. So let's consider that we are having or solving an issue with k equal to 10. So 10 nearest neighbor, and total samples that are in our data set is 1000. So is 10 nearest neighbor classifier 10 NN, and n total samples is equal to 1000. Then the volume of box, this small box, is L over D, can be given because it has D dimensions, right? And we can approximately say that this volume is is equal to k over n because it encapsulates n points, right? इसमें 10 points होने चाहिए out of our 1000 points to say that this is 10 nearest neighbor classifier, right? We can roughly say that this is approximately, right? We are approximately, and if we just simplify this L D k over n, we'll get this. If we just take d over here, d will remove and k over n power 1 over d, right? Just simple calculus. And now we can calculate how large this L would be if we change value of d, right? So we have L and we have d. We can just put values of d and find L. And here is the shocker. If L, if d, if we take two dimension, then L is 0.1. So agar this is the box, this is the bigger box, let's say this volume is 0.1. Okay, for d equal to 2. Fair enough, it's okay. But let's see, you increase the dimension of feature vector, the volume increases to 0.63. 60% of this whole is with only 10 dimension. And if we have 100 dimension feature vector, 0.955 of the box is filled. So it means that whole of this cube is filled if we have feature vector with 100 dimension. We'll need complete cube to have this 10 100 dimension feature vector. It means, and remember, n is 1000. We are dealing with only 1000 points, right? So it means that 100 points are inside 0.955 volume and rest of 0.45 volume, like just at the edges, all the 900, let's say 900 points are there because we have 1000, so 10 are inside this box and rest are at the edges. And if we have 1000 dimension feature vector, whole of this cube is actually filled. So it's 0.9954, right? So it means or rest of 990 points are squeezed between the boundaries. So there is no notion of nearness left. Everything is at the border, everything is at the edges, right? And we are just looking at, you know, 10 dimension, 100 dimension, which is very normal in machine learning, this kind of dimension. So the whole notion of closeness just goes away because of this curse of dimensionality, as it is called in machine learning. ये समझ में आया? Is this clear?
जी सर।
अच्छा, इसको एक और तरीके से भी देख सकते हैं. लेट्स से दिस इज द लेंथ, राइट, ऑफ वन, and you want point to be inside it. So let's say you want points to be inside that length. So only edges is like epsilon, right? So the probability of finding a point between these two edges is 1 minus 2 epsilon. And if it is n-dimensional world, then this would be d, right? 1 minus 2 epsilon over d. So probability of finding a point between these two. And 1 minus 2e is less than 1. We know that. And anything which is less than 1 and has a power of d goes to 0 damn quickly, very quickly. If you just start increasing 10, let's say if you have zero point 0.9 and you start changing value of d, you will feel that after 4 or 5 iterations you are just nearing 0. So the probability of finding a point between these two lines is almost 0 inside this box. So it means everything is squeezed between the boundaries. So in high dimensional spaces, everything is far away. And we are saying that we are using nearest neighbor. but there is no nearby point. Everything is almost at the same distance or equidistant. So this is really, really difficult to find nearest neighbor in high dimensional spaces. And this is curse of dimensionality. Clear?
जी सर.
So what problems do we identify? That as d dimensional increase, almost entire space needs to find 10 nearest neighbor. What does it mean? 10 points are at the edges of smaller cube and the edge of cube is almost touching outer. And rest of this 9,990 points are at the edges, right? So everything is squeezed between a small box and the big box. This breakdowns k nearest neighbor assumption because k nearest neighbor are not particularly close and therefore there is no notion of similarity. Right? So the distance between two randomly drawn data points increase drastically with their dimensionality. Neighbors are not close. All the points, whether they are in neighbor or not, are roughly at the same distance. So how to find neighborhood? Then all the assumptions just break down of k nearest neighbor. Right? So should we remove k nearest neighbor from the toolkit of machine learning? But this is not true. We are not going to remove it because there is some if we just go into statistics, we will find that there are different distributions that are ambient space is much bigger, but intrinsic space is much smaller. And when I say intrinsic space, it means where the data actually lies. Data can be encapsulated in 1,000 dimensions, but actual dimension or the intrinsic dimension of data is 10. और उसकी वो एग्जांपल है जो एक्चुअली मैंने आपको शुरू की क्लासेस में दी थी. If you take an image of a person, only face image, and it has, let's say, 18 million pixels or 6 million pixels. So if we just think there are 6 million dimensions of that image, but we don't need 6 million dimensions to characterize a person. We hardly need 20 to 30 dimensions. We can just say that eyes are like this, nose is like this, face is like this, high level information is there. So intrinsic dimension of that space is much lower than ambient space, and that we can exploit in k nearest neighbor. So this is the example, right? This space could be n dimension, high dimension space, but all the data could lie in this kind of manifolds, and these manifolds are locally Euclidean, and this manifold is like 2 dimension, 3 dimension only, and this is encapsulated in 1,000 dimension space. Let's say here kNN will work because intrinsic data itself is Euclidean and there is notion of closeness exists, right? This is the same example which I gave you of describing a person of face, right? So intrinsically, dimensionality of data is low, but ambient space in which data is encapsulated is very large, right?
Right, sir.
Okay, we are into dimensionality reduction now. Generally, when a number of features are very large, this kNN will struggle. So pre-processing data is always recommended. Here, up till now, we were just talking about their dimensionality, their intrinsic dimensionality, ambient space stuff. But let's say we have 10-dimensional data and we want to remove some dimensions, right? To know which dimension should we use. Still 10 is okay, but we want to even further remove them to find which attributes are okay to further have more efficient classifier, because 10 dimension we have to calculate dimension of all that difference in all the 10 dimensions. But if we know that out of those 10 dimensions only 3 are useful and 7 are not useful, then we can remove those uninformative dimensions from the data set and we'll work with only 3 dimensions. But how we can do it? Yeah, so pre-processing like the in our, I think last week we had the lecture of pre-processing, and one of the step of pre-processing is dimensional reduction, right? So this is pre-processing can be done over here as well. So approaches for dimensional reduction can be divided into feature selection and feature extraction. Right? Feature selection, try to find subset of input variable features that are useful. Right? So if we have 100 dimensions, we try to find, let's say, m, and m is less than 100 or very less. Right? So this is the main aim of dimensionality reduction. And there are different strategies to find which features are useful. There is a strategy called filter strategy, wrapper strategy, and embedded, which has this both capabilities. And I will explain what I mean by filtering or wrapping. Okay. Feature extraction, again, or feature projection, we can do principal component analysis for feature reduction as well. This is like if we have data, if we have data like this, and we have, let's say, high dimensional space, but we know that this data just lies on subspace. So we can project this data on a subspace to find its intrinsic dimensionality. PCA does that exactly. It finds axis with maximum spread and find its like eigenvalues. So for this data, it could be like this axis and this axis. We can project this data on 2 dimensions and we will have approximately the same distribution. So out of, let's say, this ambient space was 20 dimension or 30 dimension, but this data lies in 2 dimension, and PCA does exactly same. We will have projection of data in 2D space and reduce its dimension, and we can use for k nearest neighbor. Right? So let's say we have n features actually in our data set, and we want to find m features, which will be used for kNN. The m is less than n, and I want to ask you how hard is this problem. Is this linear problem, polynomial problem, or exponential problem? Any thoughts on complexity of an algorithm that will find subset of data set? Any thoughts on this? So this is like permutation and combinations which you have done in your calculus course. It's like choosing subset of n features which gives best score, and we'll see what I mean by score. Intuitively need to create all possible subsets of n feature. So all subset of n feature has to be drawn from m, and then we need to find like which is the best subset. So this is exponential. Exponential number of subsets are there. So we can say that complexity of such algorithm would be exponential, and this is huge. It's not easy to find subset which will give best result, because number of subsets could be are exponential actually, and you're trying to evaluate their weight, like which solution is the best given n examples, right? So in previous slide I talked about filter based approach for reducing dimensionality, and filter based approach is denoted in this simple image. So once you have all the examples or features, you pass it to this algorithm, right? And this will, like, filtering means it will evaluate them independently. Each feature will be evaluated independently based on some statistical test, and it will find whether it has useful information considering target function. So if we haven't done decision tree up to now, till now, but decision tree have a test for impurity, and this test is based on entropy of the data. So entropy means measure of uncertainty in the data. So here we can employ this kind of test based on the data set to find which features are useful considering target function. Right. Advantage of filtering based approach that this is fast. We can evaluate these features very quickly. But the disadvantage is that there is no learning algorithm. So this selection is done independently of target function. Like there is no evaluation based on target function. So classification, we have 3 class, 4 class classification. We will not test subset that okay, we'll take first 2 dimension and we'll test on a classifier whether this is good or not. This is just on statistical measures. So here the statistical test, which probably we can just verify using Pearson correlation, chi-square, Gini index, entropy. There are a lot of tests that can be done in filtering based approach. So features are scored in isolation. Isolation means they are not test for target function that is in hand or classification problem that is in hand. But wrapper approach is just opposite. It will select subset of features. It will pass through a classification algorithm to see what would be the result if we choose those M features. And it will do iteratively for all the subsets available or extracted from the dataset. And based on the result, it will choose best result. So are you getting the difference between filtering approach and wrapper based approach for feature selection?
सर रिपीट कर देंगे
आप क्या क्यूरी एग्जैक्टली पूछें? व्हाट इज द क्यूरी?
सर मैं डिफरेंशिएट नहीं कर पा रहा इसमें सबसेट रैपर अप्रोच में सिर्फ सबसेट को चूज करेगा बेस्ट सबसेट को राइट
चूज दोनों में ही बेस्ट सबसेट को कर रहा है, लेकिन फिल्टरिंग के अंदर सबसेट को वो चूज कर रहा है विदाउट लुकिंग एट क्लासिफिकेशन और टारगेट फंक्शन. So, or let's say you have 10 dimension feature, it will run over Pearson correlation, or it will run entropy, and it will find which features are most important or informative. इसके अंदर classification को कहीं verify नहीं कर रहा कि whether if I choose this subset, what would be the classification result. लेकिन wrapper based में क्या कर रहा है? It's choosing a subset. It is passing through a classification step to see whether this subset is better than the previous subset or not. So in each iteration, few of the attributes are selected, passed through classification algorithm, and tested for the target function in our. So let's say अगर आपके पास 10 attributes थे और आपने दो के इनके या तीन के subset बनाए, so it will pass through iteratively all 3 subsets or 4 subsets to a classification algorithm and see which is the best algorithm, right? जो आपका फिल्टर बेस्ड में था उसमें क्लासिफिकेशन एल्गोरिथम में पास करके नहीं देख रहा, वो सिर्फ ये देख रहा है कि स्टैटिस्टिकली इज दिस एट्रीब्यूट यूजफुल और नॉट. दैट्स इट. ठीक है.
राइट सर तो सर जो
जी रैपर बेस्ड में आप ये देखेंगे यू विल हैव अ classification algorithm. So it is choosing a subset and passing through a classification algorithm and checking its accuracy, and it's doing it iteratively for all the subsets. So you have exponential number of subsets and each subset is passed through classification algorithm and estimate accuracy is estimated to find which subset is the best subset. This is exactly same as मैंने यहाँ पे example दी हुई. You have a football team, right? या cricket की team है and all these 11 players are playing, and based on the performance you are removing some of the player in next match. Let's say you say okay, player number 10 is not playing well, so we'll drop this player 10 and we'll put this player in place of this, and you will evaluate again in next match. You will evaluate all the players and you say okay, player number 1 is not performing, so we'll drop player 1 and we'll put player 6, let's say, in the team. So you are testing in real scenarios all the time. That is wrapper based approach. ठीक है.
राइट सर
But the problem over here is for each subset, it has to pass through classification algorithm, which is very slow. slow. So you have exponential number of subsets, and each subset has to pass through classification algorithm to find. In on the other hand, in filter-based approach, there was no classification over here. Okay? It's only feature evaluation based on some statistical test. So that's why it is very fast filter-based approach. We can quickly find which attributes are useful. But if we employ wrapper-based approach, we are sure we will get better results than filter-based approach. But the drawback is it's very very slow because it has to pass through classification.
सर तो जो फिल्टर बेस्ड अप्रोच है
जी
उसमें वो टारगेट फंक्शन पे तो चेक नहीं करा, तो पॉसिबिलिटी नहीं है कि हमारे फीचर्स जो यूजफुल हो वो वेस्ट हो जाए?
बिल्कुल पॉसिबिलिटी है. That's the problem of filter-based approach. We will have suboptimal result because there isn't any feedback from learning algorithm. This is the drawback of filter-based approach. You are right. But if you want to run something very fast, then this is how it is done.
राइट.
Right? Okay. Ariba, any question? Example of this wrapper-based approach is mostly you would have heard name of genetic algorithm. There is algorithm called forward search algorithm. There is algorithm called backward search algorithm. There is another algorithm called taboo search. So there are a whole lot of family of algorithms that can be used for this wrapper-based framework. But the problem is they are right. Okay, I'll very quickly just finish this topic. We are just running out of time, and we'll see next time if you want to do. I just give this name in my few previous slides that for speeding up nearest neighbor, we could use data structure, right? And data structure is KD trees. So KD, you can employ KD tree to find nearest neighbor very quickly. So instead of looking at, let's say, 1,000 example, if your data set is 1,000 example, KD tree will boil down to like 10 data sets to find nearest neighbor. And probably we can just look at it in next class because we are running out of time and I want to spend, let's say, 15 minutes on this. Okay?
राइट सर.
Okay, let me just stop its recording for today.